Okay, so let's go ahead and get started. How many people got a head start on the Johnny homework assignment already? All right. How was it?
Very easy.
Very easy. All right. I'm glad to hear that. In a way. In a way, I'm a little bit disappointed.
Can we just print the number, see out?
You have to go through the calculations. So
yeah, but I can print like see out 96.
See out is good. See out is the way to do it.
See out 96.
See out, but you have to see out the. Okay, your program has to work with the test cases because I can throw at you.
I just did it.
Yep. All right. So are there any questions about the Johnny homework assignment?
Not yet.
Other than how do I get started? Yes.
When is it due? When is the assignment due?
Tuesday.
The homework assignment is due on Thursday.
Postpone it.
Sorry?
You promised to postpone it.
Did I?
Check the recording.
Okay. So I will postpone it to next Tuesday, right?
It's recorded, so.
Okay, the question is, did I say how much I was going to postpone it?
No.
Well, I think Moodle can go by increments of 5 minutes.
Then do 5 days, 5 hours, then 5 minutes.
Okay, I can give you guys a little bit longer to do it, but the whole point is, go ahead and do it because this is going to be a useful homework assignment to understand the other topics that we'll be talking about in this semester. So that's why it's a very important thing. We'll postpone it to 1 week from today, which is what, the 18th? Yep. Alright. So there you have it. Which basically means that most people would just postpone, getting started by 5 days, right? In fact, it will be worse. It will be by 6 or 7 days because most people will start to forget that there's a homework assignment due because it's like so far out. It's like, oh. All right. Okay, so I did write something here. This is kind of interesting. I don't think anyone in this class is particularly going to be impacted by this one here, but it's kind of interesting that okay, well that's okay. That's because I self-signed my certificate, So this is kind of interesting because if you read this article here, in some states, this is some states, entire states, there are no girls, blacks, or Hispanics taking the advanced placement computer science exam in the entire state. So I'll leave you guys to read the detail to find out which states those are. Obviously, it's not California. Well, yeah, I mean, you guys, some people back there cannot read all the smaller fonts. But there are several states, at least 2, that has this particular interesting phenomenon. If you look at the total number of female test takers, California is up there, is actually leading the country. But that's because California also starts with a pretty big base of students too. But if you look at percentage, only about 21% are female out of all the students who took that test. But it's still better than none, 0, zilch, nada. So that's kind of interesting. The other one, I wrote some of these things. This one has to do with Flappy Bird. I have heard enough about Flappy Birds. So, I think it's time that someone actually write a useful or at least fun to play game. And I'm thinking about a Turing game, where you can just kind of use it like this, and it will point to the direction that you're pointing it at.
No, he's talking about an AR game.
I think the Nintendo 3DS can do that.
Yeah.
There are games like that already.
It's actually loaded on it by default. It's like an AR game where you can.
Augmented reality.
Yeah.
Yep.
Stuff shows up in your living room.
Yeah. Well, it would be kind of nice if they can process the camera fast enough. They can actually recognize people in a room, and then overlay zombie images on top of those people. So that would be kind of cool. This one is kind of interesting too because we keep talking about Linux in this class. We keep talking about Linux in this class, but there are people out there who are still using Windows 98 and Windows XP. And it's the TSA. It's in their X-ray scanners in the airports. They're still running Windows 98 and XP, which obviously is not the most secure operating system available today, at least, right?
Walmart.
But the good thing is, those machines are so old that they are not Wi-Fi enabled. So there's no worry about getting hacked, through the network. People actually have to walk up to the machine to physically hack it. There's no other way to hack these machines. It's not like you can just Bluetooth into it or Wi-Fi into it and hack it. Yep.
So they're inherently secure because they're old.
Security by obscurity, yes. So that's kind of interesting. And of course, the last one I saved the best for last. How can we put up these three terms in the very same sentence? Elmo, Captain Kirk, and Linux. Some of you know this already, but I would suspect that some of you, have been too busy with your homework assignments, like Johnny, and have not kept up with the news. So I'm going to show you a picture.
That's definitely the reason why I haven't kept up with the news.
So this is the reason. This is the USS Zumwalt. That's it. And Elmo is the first name of Admiral Zumwalt. Okay, so there goes Elmo. It's not the Sesame Street character. The second one is Captain Kirk. As it turns out, the captain of this new ship is Captain James A. Kirk. Now, for those of you Trekkies, you know that the character is James T. Kirk, not James A. Kirk. But it was pretty close, okay? First name and last name both matched, except for the middle initial, okay? So that's kind of interesting. Linux. This is a floating Linux data center, basically. It is a warship, it's a destroyer, but at the same time, they put a lot of processing power into the ship. The consoles are more like Star Trek, but not talking about the original Star Trek where everything is really tactile, right? They make all kinds of sounds. I'm talking about the next generation where they can move the console they can move a control program from one console to the next. And this one, this ship can do about the same thing. So it's kind of cool, things are moving in a, interesting direction. They chose the Navy, or the contractor, Raytheon, decided to use Linux instead of Windows or any other operating system on the ship. Okay, now, why is that even significant to you guys? I mean, I would suspect that a very low percentage of this class would actually end up, enlisted and serve on a ship like that. So why would that be even be interesting to you? Hack into it? Hack into it? Well, with this ship, because so many systems are already automated, and the computer system is network capable, whether they want to hook it up to the network or not is a whole different story. So I would suspect that Captain Kirk can remotely pilot the ship, from when he's on vacation. So they will still need people on the ship, to do certain things. But for the most part, the command center can be remotely controlled. So I would say, he probably has an app called Zumwalt, app, right? So you can just kind of drag and drop the ship, and then everybody on the ship would go like, "Whoa, why are we turning?" But okay, getting back to the serious part, I think it has to do with jobs. Raytheon is not a small company; it's a big defense contractor. Okay, so when a big defense contractor who has a lot of requirements to meet is starting to use Linux as the base, operating system, I'm thinking that there are employment opportunities out there when you know how to use Linux, or when you know, the core part or the kernel part of Linux, because they really need to improve. They need to make sure these operating systems are secure, and that's not a small job by itself. And then on top of that, you also have to work on communication, make it more reliable, make it foolproof, make it bulletproof, and so on and so forth. So I think there are lots of jobs related to that. This will prove it. Well, go ahead and read the documentation on this chip. It's really quite interesting. They did not go conventional at all on multiple design procedures. So they decided to do something entirely different. They originally wanted to build 22 of these chips, but because of the expenses and probably politics too, now they're only going to build 3 of these. Yeah, so they shrunk from 22 to 19. But it's a proof of concept. I think for the most part, this is a proof of concept about stealth technology, using Linux as an operating system, and amongst many other attributes of this particular destroyer. So it's kind of interesting because now Linux is getting into cell phones, it's getting into tablets, that, and what else? I mean, pick a niche that Linux is not into right now.
You can't. You can't.
It's difficult. It's difficult. Yep. All right. So there goes all the kind of fun stuff. So this is the Johnny homework assignment. If you have any questions, we can talk about it when we go to the lab. Otherwise, I'm just going to assume that people are starting to work on it and not have any questions about it. But it is an important homework assignment. This is a really, really important homework assignment. So without any other discussions anymore, the binary add homework assignment, I'm not going to assign it. It's still useful to do it, but it's not. I'm not going to assign it. So are there any questions about the topics that we have talked about so far, in this class? No questions? Okay. Has anyone started to read about the memory cycles? I think it is in this note here. Okay, let's start with this one here. Okay, the story of registers. And in Johnny, which part of Johnny do you think is a register?
Accumulator.
The accumulator, exactly. The accumulator is the only register in the Johnny processor. Now, throughout history, there are processors out there with only one register. One particular processor is also kind of famous because of its popularity in personal computing, early personal computing. Which processor do you think I'm referring to? It's not the 8086 processor, because that one does have multiple registers to begin with. Z80. The Z80 is based on the 8080, which is the granddaddy of both families of processors. So it had multiple registers already. What about the Apple II computers? Which processor did it use?
6502.
6502, very good. The 6502 technically only has one register. It does have the XY register for indirect access, but for computation purposes, it only has the accumulator. They name it the accumulator, just like in Johnny. So let's go ahead and take a look at this particular module. We'll start with the ALU. The ALU stands for the Arithmetic and Logic Unit. It's probably going to be helpful to kind of bring up Johnny too at this time. So I'm going to go bring up Johnny. Okay. This saves me a lot of work because I don't have to draw the pictures now. Otherwise, I will have to draw the pictures. Yep. Okay, so here's Johnny, and the accumulator is the one on the right-hand side. Most of you can probably see where the accumulator is. This is the accumulator. This is the only part that can keep up with the clock speed of a processor. In other words, as fast as your clock can click, the accumulator is not a bottleneck of performance. Okay. Where's the logic to do calculations? And by the way, what kind of calculation can Johnny do?
Plus, minus.
It can add two numbers. It can subtract one number from another number. What else can it do? If you just look at all the buttons, that would give you a pretty good clue.
Increment.
It can increment and it can decrement. That's it. That's basically all of the computations it can do. There's one that's kind of extra, which is equal to 0. In other words, it can check whether the number in the register accumulator is 0 or not. That basically are all the computations that you can do. Everything else has to do with just moving things around. Like DB to ACC is databus to accumulator. ACC to DB is accumulator to databus. So those are just really for moving things around, but not for computation. So for computation purposes, you can zero the content of the accumulator. You can add 1 to the content. You can subtract 1 from the content. You can add content from the databus to the accumulator. You can subtract content or value from the databus from the accumulator. And that's it. Okay? Basically 5 operations, or including 6 is the test for 0 operation. So those are the things that are hardwired and connected to the accumulator as a register, so that operations like those can be performed. Any questions about this? But those operations can be very, very fast. The ALU can only compute. It has no practical storage ability because it can only do computation. In other words, when we are talking about computation, we are actually talking about this. These buttons here are doing the computation. The accumulator is actually going to be used for storing the temporary result after the computation. All right, moving up. Okay, so where are we going to store the data? Well, one idea is to store in memory because we have gigabytes upon gigabytes of memory. So there's plenty of stuff, or plenty of storage. There's only one problem. If you want to use external memory, in other words, the memory that you buy from Fry's, in the dual inline memory module form, if you want to use that to store everything, we have a big problem. It has to do with how slow it is to retrieve anything from memory and how slow it is to store anything to memory. By today's standard, what is the fastest memory you can buy at a regular store like Fry's?
2205.
Sorry? 20 DDR5. But what is the data rate?
2200.
2200. Okay, so 2200 is rated by as what? 2200 mega transfers per second, right? That's usually how memory is rated, is 2200 million transfers per second. So that's how fast your memory can transfer. Can it sustain this kind of transfer rate? No. It cannot sustain this kind of transfer rate. And what is the most basic transfer rate, if you cannot do pipelining and all the burst mode transfer? It drops down to what is the clock speed of the memory bus? Say again? 400 megahertz? Okay, is that about right? Clock speed of a memory bus?
For an Intel processor, yeah.
Okay, so 400, let's say it's 400. Okay, so 400 megahertz is the clock speed of the memory bus. So now the question is, how can we get this kind of transfer rate when the bus or when the clock speed is only this slow? In other words, the clock is the basic timing mechanism, click, tick, tock, tick, tock. And it can only occur 400 million times per second. But according to this information, according to the rating of memory, we can transfer 2200 million transfers per second. So how can that happen?
You need multiple bus.
You need to have multiple transfers per clock, right? So basically, in the good old days when the DDR first came out, it is basically for every rising clock, it can transfer. For every falling clock, it can also transfer. Instead of every rising clock, every rising clock, every rising clock. In other words, when you look at memory, the clock looks like this. It's a square wave. Before DDR, you can only perform a transfer on the rising clock or the rising edge or the falling edge. DDR, when they first came out, it means you can do transfer at a rising edge and also at a falling edge. Now later on, they also added transfer cycles in between the edges, and that's how you can perform multiple transfers using this type of method, using this kind of technique, even though the clock speed itself is only 400 megahertz. Is that okay so far? This is just a general introduction to the how modern memory bus works. Okay, well, that's great. But there's a problem with this understanding, because even at this transfer rate, this is not sustainable. It is what we call the burst mode transfer. It is not the usual transfer. Okay, let's think about what happens when you need to talk to memory. And there's a little discussion here too. Trying to find out where I put the memory cycle stuff. I wrote all this stuff and then I cannot remember how I organized everything. It's okay. We can just go ahead and write it out here on the whiteboard, so this way it's going to be recorded. So let's think about when we look at Johnny, it simplifies a lot of stuff. In other words, in Johnny, in order to write to memory from the accumulator, this thing here happens, ALU to data bus, and then from the data bus, the data is already presented here, and you just need another operation, which is DB to RAM, and that will write it. But before that happens, you also have to latch out the address. So the address bus has to have some kind of content to specify which page or which location we are writing to, and that can be done either by INS to AB, which is command register to address bus, or PC to AB, which is program counter to address bus. Either one will specify a address. The memory content here would understand, okay, you want to access this location, it is now ready. So the next operation is either to do a DB to RAM or RAM to DB to either write to memory or read from memory. Okay, but this operation is greatly simplified. So what I'll do is I'm going to introduce the actual individual cycles in memory access so that we can see the detail of what needs to happen in order to just to write to memory or just to read from memory. And also from that, you can start to realize why this is an ideal number, but sometimes depending on how your program is structured, that speed may not be attainable at all. Okay, so the first step is the processor. Okay, so let's talk about a write cycle. A write cycle is seen from the perspective of the processor. So we are looking from the perspective of the processor. We are writing content to memory from the processor. A write cycle typically starts with specify address on the address bus. That's the first step. The second step, once you have the address on the address bus, then you can specify whether it is a read or write operation. Specify read write operation. The third step is to assert chip select. Chip select is a particular line, I'll explain that later, but I just want to count the number of steps at this point. So chip select is going to be asserted, and then step 4, okay, actually I messed up here. Number 3, present data to be written on the bus. This is step 4, assert the chip select line, and those are the steps involved in writing to only one location. Okay, so let's take a look at these operations, and then we will take a closer look at how memory is actually organized. Okay? Let's say you have 16 gigs of memory on your accessible to your processor. From your software perspective, you just say, oh, it's a linear array of 16 billion bytes. It's a huge array of memory locations, and each one is only 1 byte wide. But when you look at how it is actually organized, it's not really organized that way. Okay, when you look at the number of lines or number of traces on a dual inline memory module, how many lines do you think there are with one single module? how many pins are there, on one single memory module? It's 100 and something. Okay, I cannot remember how many, but it's
184 or 240.
it's more than, it's 200 something now, right? Isn't it?
240, I think it's more.
240, 240 pins. So there are a lot of lines there. So what is going on? Well, as it turns out, we do not have, a linear memory space when it gets down to the hardware level. I'll explain it like this, okay? So what I'm going to do is I will say there are 4 banks or 4 individual memory modules in the memory subsystem. Okay? Each one has its location 0 and has its maximum address location. So for the purpose of this discussion here, we'll just say that in hexadecimal, 3FF is the highest address on each chip. Is that okay so far? Okay. Can someone quickly tell me how many locations are there in decimal when 3FF in hexadecimal is the highest address and we are counting from 0? Okay, 100 is 256 because it's base 16. Okay, 100 in base 16 means this is counting 1, this is counting 16, and this one is counting 16 squared, which is 256. Is that okay? So if 100 is 256 in decimal, what do you think is 3FF, which is pretty close to 400? It's 1,000. It's basically 1024 locations. It's 4 times 16 squared. No, I take it back. It's 16 squared. No, it's 8. 16 times 16 is 56. Okay, that's right. Okay, so this is actually, if you want to count from the perspective of decimal, it goes from 0 to 1023, which is the highest location. Okay. So now we have 4 pages here. The only reason why we cannot have one single chip sometimes has to do with the density of a chip. We cannot put all the memory that we want to have in the system on a single chip. It's just not big enough for that. So that's why we have to divide it into multiple chips. So this is physical. This is the hardware side. On the software side, let's say I want to access location. Let's see. I'll make it easy. So let's try to access location 850 in hexadecimal. So we have 2 ways to represent hexadecimal. In C, 0x, as a prefix is a way to represent this as a hexadecimal number. So this is from the logical perspective. This is the logical location, and this is representing the physical side of memory. Which chip do you think is responsible for that location? Not the last one. Okay, so if you think about it, if we start from the left and then we move our way to the right-hand side, this one is responsible for location 0 to 3FF. This one will pick up from 3FF. So that means it's responsible for location 400 to 7FF. This one is now responsible for location 800 to BFF. BFF because in hexadecimal we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, so BFF is the correct one here. And this one goes from C00 to FFF.
Wait, why C00?
Because this is the last location on this chip. Okay. So this one is one more than the last location on this chip. Is this still doing okay? The translation from logical address to which chip I want to access. Right? So 850 belongs to somewhere on this chip. In fact, I can find out exactly where on this chip because on this particular chip, I want to access location 50, not 50, 50, because 50 implies it is decimal. 50 simply means it is 5 and a 0 in whatever base that we are using. not nitpicking, because I just want to make it as clear as possible. This is not 50 in decimal, it is 50 in hexadecimal. Okay, so we now know that the location that we want to access is this location on this particular chip. The question is, in terms of the memory bus cycles, what are we going to do on the address bus in order, and also chip select, in order to perform this operation? All right. So does everybody understand what I'm trying to explain here? Okay. The first step, according to the right cycle, is we want to specify the address on the address bus. So what address am I going to specify on the address bus? Now keep in mind, the address bus is a broadcast type of bus, which means all 4 memory modules will see the same address bus. If you latch out an address, all 4 will see the same address. But the memory modules are not active until you say, hey, I want you to do something. Okay, so until you point a finger to the chip and say, you are the one that I want you to do something, nothing happens. So the address that we want to latch out on the address bus is actually 50 in this case. Okay, so in this case we latch out 50 in hexadecimal onto the address bus. But that's awfully confusing because all 4 chips are listening to the address bus at the same time. So this chip, the first chip, will say, hey, okay, I'm going to prepare that location. The second chip doing the same thing. The chip that we actually want to access will do the same thing, and the last chip would also do the same thing, because they are all listening to the address bus and it has the same content across all 4 chips. Okay, so that means the first chip will go to this location and say, okay, I think I'm ready. Okay, the second chip will go here, and so on. Sometimes they may not even pay attention until the chip select line is asserted. The data bus is also global. Okay, it's basically kind of like a global variable, which means you have the same data bus going to all of the memory modules. So what is the one thing that is not going to all of the chips? The chip select line. Okay, this guy has one chip select line. This guy has one chip select line. This one has one chip select line. This one has another one. And those 4 chip select lines are separate. The memory control module, or the memory management module on the processor, is responsible to use this address to figure out which chip select line should be asserted. Are we doing okay, kind of? Okay. So after we specify the address bus content on the address bus, in this case it is 50 in hexadecimal, we specify this is a read-write operation, and once again the read-write operation is specified by one single wire that is connected to all of the chips. It depends on the chip, but most of the time it is a high signal means it is a read, and a low signal means it is a write operation. Okay? But that is just, it's somewhat arbitrary, which one is indicating a read operation, which one is indicating a write operation. Step 3, you present the data that you want to write to the data bus. So now the data bus has content on it. The very last step is to point to one particular chip using the chip select line and say, you here, I want you to actually perform the operation. So only at that time, this particular chip will go to its location 50 in this particular chip and use whatever content is specified on the data bus to overwrite the content of this location. Are we still kind of doing okay with this? Okay. Do you think that's a really fast operation with all of these steps?
Yes.
Nope, it's not a very fast operation. It takes time to latch out content onto a bus. Okay, and by the way, what exactly is a bus? When you open up your computer, can you actually visibly see at least a part of the data bus and the address bus?
Yes.
Yep, and it is indicated, yep, exactly. They are basically, we call those traces on the motherboard or on the circuit board. They're basically just a trace or a line of copper on the PCB or printed circuit board. Okay, And how big is your circuit board? You know, we can think about the smaller ones too. You know, these days we have really small circuit boards. So approximately how long do you think is the trace going from memory to the processor? I would say at least a few inches. Would that be a kind of like a fair assessment? Okay, a few inches. A few inches doesn't sound like a lot, but when your signal is going at a very high speed, in other words, it's going to change at a high rate, a few inches is a lot of wire. Okay, how many people have taken a physics class already on electromagnetics? Okay, so what exactly is a wire? When you look at a single conductor, how do you model the behavior of a single conductor?
Kind of moving around, it's like floating.
It has three components. Okay, there are three ways to quantify the characteristics of quote-unquote a wire. What are those three things?
Area, surface area.
From the electrical perspective.
Resistance.
Resistance, all right, that's a good one. So when you look at a wire, there is an inherent resistance to the wire. Okay, nothing is a perfect conductor. So that's why everything has a little bit of resistance to it. Now with 4 or 5 inches of copper, the resistance is negligible. That's not our problem. Yep.
Resistivity, length, and cross-sectional area.
Okay, those are the physical characteristics. But in terms of electrical term, sorry?
Inductivity and capacity.
So we have capacitance, and we also have inductance. Exactly. Okay. So all of those things, I cannot remember whether they're. I don't think they're parallel. I think they're supposed to be in series. Except for the capacitance, that's actually in parallel. But anyway, there are these three components. When we think of a copper wire, and we flip a switch like a light switch over there, we think of it as a perfect conductor, right? You flip it on, and electricity goes to the lights, and it lights up the room. But when you are talking about high frequency or signals that are changing rapidly, now these things start to become important. How do you model an inductor? In other words, if you look at an inductor like this, and you say, okay, I'm going to apply a certain, okay, let's put a resistor in series. So once I apply a certain voltage here, and this is ground, does current instantaneously start to flow and only be limited by the resistor? Nope, because one way to look at an inductor is it's a flywheel from the electronic perspective. Okay, it takes time to spin up. Okay.
Did not change the current.
Exactly. So you have to ramp up the current because of the inductance. So those 4 or 5 inches of trace on the motherboard, on the printed circuit board, has all of these characteristics as well. Now this inductance is negligible when we're talking about lights like these, or just a switch or the wiring for these lights. But when you're talking about a very high frequency signal, they become important. How do they affect the ideal waveform of a square wave? Because what we want to do is we want to send waves like this on those traces. What do you think capacitance and inductance together how do they change these things?
Like wave.
Okay, so there's no sharp
sharp
edges
edges.
anymore. So they become sharp waves, what we call sharp waves. And when you turn it off, it doesn't turn off all the way. With capacitance, this is what you see. Okay, they are just kind of rounded off a little bit. Okay, and with inductance, when you turn off something, it will get you get spikes here and also down here when you suddenly try to change the signal. In other words, the faster it goes, the more rounded it looks like, and the longer the trace on the printed circuit board, also the more round it's going to look like. And that really is the limitation of how quickly you can move bits from one location to another location on a printed circuit board. The same thing applies inside the processor too, except because of the much shorter distances, it is not as pronounced as these waveforms on an actual trace. Okay, so that means just to make sure that your address is correctly specified on the address bus, takes time. What kind of time are we talking about? It's the time from here, from the time that the processor says, okay, I am going to specify the address on the address bus, to the time that the address is actually reliably specified on the address bus. And there's no way to get around this problem because it is the property of a trace on your printed circuit board. Are we doing okay so far in terms of just having a basic understanding of why there's latency just because of the wiring on the circuit board? Now, once you get to the memory module, okay, so now let's say we look at this as a memory module, and there are pins here and pins over here. Some of these are pins corresponding to the data bus, other are pins corresponding to the address bus. We have a read-write signal, and then we have a chip select. Those are the most basic pins to a memory module or memory chip. But once the signal comes into here, we have a lot of logic here, inside here, flip-flops, latches, and so on and so forth. And those things also have their own propagational delay. In other words, from the time that this pin actually sees this line reliably to the time that the location on the chip is properly addressed, there is another latency. But that's inherent to the chip itself. And as a result, you cannot perform those 4 steps as quickly as you want because you have all of these physical constraints and there's latency in between. Are we still doing okay so far with the concept of, well, there are 4 steps to perform in order to write content to a single location, and we cannot get it done really, really quickly.
So they address another chip. While this chip writing, they address another chip for writing.
You can, so are you talking about pipeline or just having more chips being written to at the same time?
I'm saying if writing takes a lot of time, long time to write something, so processor address another chip to write the second piece of information.
But it's using the same bus, that's the problem. You only have one data bus. So when your data bus is being used to write information to one chip,
but
you cannot use it.
Writing is synchronically with database frequency, or it's slower than bus frequency?
This is going to occur at bus frequency. So at 400 hertz, we are going to clock out those particular steps because they need to be synchronized. In other words, you need to make sure that you leave enough time for the memory chip to actually perform the operation.
I just thought maybe chip perform operation a few tasks, for example, 8 tasks, chip just writing inside, like I know flash memory works not in synchronically.
Flash memory takes a long time to write because the inside the flash memory is actually another circuitry just to overwrite, or it cannot really write to a single location. That's the first thing about it. You have to overwrite the entire block. So that's the first thing, and then it takes a long time for the write operation to finish as well when we're talking about flash memory.
But that memory work on bus frequency.
This is working at, I would say it's close to bus frequency, but not quite. Okay, it might take 2 clock cycles to finish those 4 steps. Okay, so that means but how do we attain this kind of insane transfer rate when the clock speed is only this fast? There's a trick to it. Okay, the trick has to do with we don't want to have to deal with these 3 steps, or the first 2 at least. Okay, because if you're accessing locations in memory that are adjacent, there's a trick. There's a trick to it. Okay, and that's actually the original DDR concept. So let's say we want to access location 50, 51, 52, and 53. Okay, so I want to access 4 locations consecutively. Okay, when we do not have any tricks, then we have to specify the address. 50 go through those 3 extra steps. 51 go through those goes through those 3 extra steps. 52 and then 53 in order to access 4 consecutive locations. DDR memory has an internal logic to say, okay, if you want to switch to burst mode, let's do that. Okay. In other words, it can communicate. The processor can communicate with your DDR capable memory and say, let's do it in burst mode. Now, what is burst mode? Burst mode basically says, okay, let me specify the first address that I want to access. Okay, so we still have to specify 50 on the data bus and specify this is a write operation. But after that, the magic happens. Because then I can just say, okay, here is the data for the first location, here's the data for the second location, here's the data for the third location, and here's the data for the fourth location, with no communication or lockstepping in between these steps. We do okay so far. Now that is really tricky because what we are talking about here is once we specify the initial location to start the burst mode transfer, we have, the data bus changes at this point, the data bus changes at this point, the data bus changes at this point, and the data bus changes one last time at this point here. But there's no handshake between the processor and your memory module. Your memory module has to keep track of an internal clock that is synchronized with the memory clock itself in order for these steps to lockstep. What if you purchase memory that is a little bit too slow? What do you think will happen? Your processor doesn't care. Your processor, once you tell your processor that the latency of a particular memory bank is a certain number of nanoseconds, what's going to happen is your processor will time these things accordingly. 1, 2, 3, 4. Okay? Your memory module, on the other hand, would look at this memory, would look at the data bus at this point, try to make changes. Now, if that change takes longer, in other words, if it takes this long for the memory write, for the first memory write to become effective, by the time it samples the data bus, it's already a little bit late. Okay? And if this is also late, it will push the time out, and eventually it will be out so far they will miss one update from the data bus. And that's why when you purchase memory, how do you specify memory when you purchase memory these days from Fry's or some other, whatever store? Remember CAS and all those other numbers?
Oh, yeah, latency, 88.
Exactly, that's basically what the latencies are. So for each type of operation, there is a latency associated with it. Okay, so there's a latency associated with specifying the address on the address bus. There's another latency for reading it. Okay, if we want to read a location from the time that the chip select actually asserts to the time you get the data back on the data bus, there's a latency. So that's why when you specify memory, there are all these numbers. They are basically all latency numbers to specify how much time it takes for each sub portion of the memory cycle. And that's the stuff that we don't see because for the most part we just go by the overall rating of memory. So all the DDR technology, they are DDR5 is an improvement over the previous one, but the basic technology of DDR or double data rate initially is the fact that we can perform multiple operations but without having to latch out the address again because they are affecting only consecutive locations. Is that okay so far? Okay, but it is still a slow operation. If you want to do random access to memory content, it is not going to be fast. In other words, if you want to access random locations in your memory, it is not going to be able to sustain this kind of speed because that is theoretical only in burst mode. If you're not in burst mode, that number is not even close. Are we still doing okay so far? Now this is a pretty huge number. If you think about it, it's 2.2 billion transfers per second. And each time we transfer, we're transferring 128 bits or at least 64 bit, right? So we are transferring a lot of data, in a very short amount of time. But how does this number compare to the processing power of your Pentium i7 processor with 4 cores, which by today's standard is what? Medium end, medium high-ish. It's not even insanely fast anymore, right? 4 cores is like, that's about what most people want. Okay, so if you compare this kind of transfer rate to how fast a processor can process, how do you think this number compares?
Not very high.
It's not quite that high, is it? What is the clock speed of an i7 processor?
3.5.
3.5 gigahertz. Okay, so we are talking about, okay, let's take a look at these numbers here. 3.5 gigahertz, which means 3.5 billion clock cycles per second. What is the fastest instruction? How many clock cycles does it need to complete? Single clock. Okay, so we are talking about, in theory, we can perform, each ALU can perform 3.5 billion operations per second. How many ALUs do we have? No. We have 4 cores. Each core has how many ALUs? If we are talking about integer ALUs, I don't know for sure. We can look it up, but I can assure you it is in at least 4 or 5. Okay, Okay, so we'll go ahead and take a look at number of ALUs per core. Let's make it more specific. I7. Okay, I think I just saw 6 operations per cycle. There we go. Okay, previously, so this is not even the modern one. Previously, Intel's architecture was able to execute 6 operations per clock cycle, and this particular architecture gets 2 additional ports, 1 integer ALU and 1 store, enabling up to 8 operations per cycle. Okay, so if you look at this number, and that's on a per core basis, and then you have what, 4 cores. So we are talking about tons of processing power when it comes to when we compare to how fast we can feed the processors. Are we doing okay so far? Yep, go ahead.
So if there is one data bus between the RAM and the processor, what's the dual channel memory gains?
The dual channel, I think, makes it wider. Is that how it works?
Is it like read and write at the same time?
No, it is it's widening the bus, which means instead of reading 64 bits at a time, it's reading 128 bits at a time. So it's basically, it's doubling the amount of, the bandwidth or the amount of memory you can read per second. Yep.
So the ALU, is that like a physical aspect, or is it like?
The ALU is inside the processor. It's basically, the actual circuitry that performs calculations. Do you still remember the half adder thing? The gates that we used to specify, half adders and then the half adders and the full adders. The ALU basically has circuitry like that, not exactly using the way we implement it, but it has circuitries like that to perform, simple calculations like addition, subtraction, and so on and so forth. So the ALU is not, it doesn't have any memory. Once it performs the calculation, it has to store the result of the calculation in a register, or it has to store it all the way back into memory, but it cannot store anything. It's just it's just for calculation purposes.
Okay, so I'm not sure, but hyper-threading, does that have to do with ALUs too?
No, hyper-threading is a different type of technology. With hyper-threading, in an ideal situation, from the software perspective, it is almost like you have twice the number of processors. It makes multi-threading or switching thread really, really easy, and therefore improving the speed. It's using the spare resources available. When it optimizes the processor to make use of parallel processing as much as possible.
I'll just make it.
Okay, so now I think we have a fairly clear picture that the processor can outprocess how fast you can feed it. Is that okay? Does everybody kind of get an idea that your process is much faster? So an analogy to help you understand how slow memory is kind of like, so let's say I am the ALU here. Okay, I'm the ALU, I have a little calculator because I have no memory. Remember, an ALU has no way to store anything. Okay, so all I can do is, you can give me 2 numbers, I will do the calculation, and then I can, give you the sum of those of those two numbers, and I can do it relatively fast. Okay, so let's just say that it's human speed. Okay, so we are talking about human speed. You write down two numbers on the whiteboard. I can punch it into the calculator, and on my calculator, I will have the answer. Okay, and that's how fast I can do calculations. So within that scale, if I need to store that number into memory, it's kind of like, you know, writing that number on a little piece of Post-it and ask one of you and say, okay, you need to go to the library, 3rd floor, this shelf, and over there to store that number. Okay, so while you're doing that, I'm just going to stay here and I don't have anything to do, right? And when you come back and they'll say, oh, you know what, I want you to go get the next instruction. And by the way, it is in the library, on the 2nd floor, this shelf, on that book, just give me that page. Make a photocopy and come back so I can know what to do next. Okay, not quite that bad, you know, but you know, it is an analogy of how slow memory is. So if everything that you do needs to access memory, your i7 processor is just going to be sitting there doing nothing for the most part. Okay, everything is going to be memory bus bound. Okay, so how do we speed things up? The first thing we do to speed things up is the use of registers. Now, what exactly are registers? Registers are kind of like a whiteboard here. Okay, do you think this whiteboard can store as much content as the library? Not even close, right? But if I just want to do some calculations, the whiteboard is really useful because I just need to keep track of, let's say, 6 or 7 numbers at a time. So the whiteboard is quite big enough for, you know, keeping track of 6 or 7 numbers. So if I have access to a whiteboard on top of a calculator, I don't need you to go back and forth to the library all the time because now I have a way to store the intermediate results of my calculation. It's only when I really need to store something or when I need to get something like the part of the program, then I need to ask you to go to the library again because I cannot store that much information on the whiteboard. But it significantly speeds up the whole processing. In the ALU, if I go to the Johnny simulator, the ALU, inside the ALU, the accumulator can keep up with the calculation. So as fast as the ALUs can perform calculations, the ALU and registers in general can keep up with that speed, which is really nice because now, you know, we don't have to worry until, you know, I run out of space in the registers to store my information. How many registers do you think we have on the i7 or the Intel processor in general? Not the width, just the number of registers. Say again? There are 8. Okay, there are 8 registers that we can actually use, you know, on a regular basis. There are more registers than 8, but if you just want to do calculations, addition, subtraction, and whatnot, there are only 8 registers available. Do you think 8 registers is a large number or a small number by comparison to other processors? It's a small number. And why do you think that is the case? Say again?
Are they optimized for Windows?
It has to do with Windows.
It's the x86 architecture.
It's the x86 architecture. So when you look at the history of the x86 architecture, it started off with the 8080 processor. The 8080 processor evolved into the 8085 processor, and at which point, I think at this point it's split into the Z80 processor and also the 8086 processor that we know. This one is actually superior, but for whatever reason, IBM chose the other one, you know, and not the Z80 processor. So the Z80 processor actually ran CP/M, you know, at its time, and it was a fairly capable operating system. And DOS was basically a clone of CP/M initially. Okay, and on the other side we have 8086, which is the 16-bit version of the enhanced version of 8085. But the early PCs run the 8088 processor, which is the 8-bit version of the 8086. Basically, inside the processor, it can perform 16-bit operations, but the external data bus is only 8-bit with the 8088 processor. So it needs extra time to write and also read from memory. From here, the next PC skipped the 186 processor, so it skipped to the 286 processor. There is a processor in between, it's the 186 processor, but it has a certain modes of operation that is not upward compatible with the 286. And it is only until we get to the 386 processor that things start to settle down. Okay, now we start to have virtual memory. Now we start to have 32-bit registers, 32-bit operations inside, and so on. And then from 386, we move on to the 486 processor, and nothing really happens. Not a whole lot of stuff happens between the 386 and the 486. But for the 486 to the next one, which I think is the
686.
686? No, there's a 486.
No, after 486.
After 486 is the Pentium, right? The code name is Pentium at that point. So there's nothing from Intel between 486 and Pentium. There's nothing quote unquote in between. And this is also a significant change because up until this, okay, I should point this out first. From 386 to 486, it was actually a significant change because that was when they finally was able to put the FPU, the floating point unit, onto the same die as the main processor. In other words, before you have a 386 processor as the main integer processor, but every time you want to use hardware accelerated floating point operation, you need to buy and install a separate chip called the 387 math coprocessor. Okay, and some people will remember the 486 also had a floating point coprocessor in quotes.
It calls SX.
The SX is the one without floating point ability, right? But they also sell a 487 coprocessor that you can install on the motherboard so that you can have floating point unit again. But the 487 processor is nothing more than a fully capable 486 processor. It has to do with when they manufacture these chips, the chip was big for the time, and the manufacturing technology was not mature at that time. So a lot of times they have manufacturing defects on the die, and the defect almost always is on the floating point unit. So, so when Intel tested all these chips, they would basically look at all these chips and say, okay, this one failed, this one failed, this one failed, this one failed, this one passed, this one failed, and they look at all the chips that have failed and say, wow, that's a lot of chips. I mean, if only if we could sell these chips also. And then they found out, okay, but what is wrong with these chips? Floating point unit, floating point unit, floating point unit, floating point unit. Okay, we'll just go ahead and use a laser to cut, the circuitry of the floating point unit from the rest of the processor, and then we'll sell this processor as integer capable only. Okay? So what if you bought a integer capable only 486 chip, and then later on you say, okay, I have to do a lot of calculations in floating point unit. I want to improve the ability. You buy a 487 processor chip, which is basically a fully capable 486 chip to begin with. And when you install that chip, it just takes over the entire bus. It takes over everything.
But why do you have two of them? Why does that not have like 47 or 46?
Sorry?
Why have an extra one there, the 47? Why not just remove the 46 from that and put 47 there?
Because they don't want people to know.
Oh.
That's basically why. Okay? And then the Pentium processor truly have floating point unit inside because by that time they have perfected the technology to manufacture chips and not have a whole lot of problems with the floating point units. Okay, but looking at this path here, my whole point is there's a long history, okay? There's a long history here. And where does the software backward compatibility ends? In other words, from the Pentium, we have the dual core. For the dual core, we have the i3, i5, i7 processors. So we have a long history, not counting architecture change, not architecture, but fabrication change within the same family. Okay, because even within the i3, i5, i7 processors, they change the how do you call those terms? How do you term those things?
Because it's already fourth generation of 5.
4 generations. Okay, let's call it. Yeah. So there are individual generations within each family as well. So there's a huge long history here. Instruction or opcode backward compatibility goes all the way back to where?
86.
Goes all the way back here. So that means whatever instruction we specify here, it needs to have I take it back. Whatever instruction is specified by this architecture, the hardware of your modern processor has to be able to recognize it. Okay? And that locks down the number of registers. Because remember, opcode is just a whole bunch of zeros and ones. But within all those zeros and ones, they have specific chunks to specify which register do we want to use with this instruction. And the way it is it is only 3 bits. With 8 registers, you can specify which register to use using only 3 bits. But that became a part of the intrinsic structure of an opcode. The binary opcode of an instruction, that became a part of it. Which means when we continue and keep improving, keep strengthening the transistors and speeding up the processor, we cannot change that intrinsic limitation of each opcode can only specify one of 8 registers. And that's why the Intel processor, even to date, has a fairly small number of registers compared to other things like ARM processor. The ARM processor has 32 registers, okay? So it is a much larger number. In other words, you have a much bigger whiteboard to store intermediate results. Are we still doing okay so far with this discussion here? Okay. And the Intel processor is actually kind of like this in many ways. In other words, these are instructions that we know, okay, in the x86 instruction set or 386 instruction set in this class. Each instruction is fed into the instruction register, but from that point, it is going to be translated into microcode. So the Intel architecture, the core inside each Intel processor, is actually capable of, I would say, a lot faster, in terms of processing power per watt. It is actually much more capable than what we can observe if we can just rewrite the microcode and use a different instruction set. But that is not an option, because if you do that, then you lose backward compatibility with everything that Microsoft has written. Yep.
Why is no one wanting to break that backwards compatibility?
That is not a question directed to Intel. It really is a question that you should direct to Microsoft. And the interesting part is, Linux is also an operating system. Okay, in terms of complexity, I would say, the core or the kernel part of Linux and versus Microsoft, the anti-kernel, I would say they're about comparable. Okay, one is not significantly more complex than the other one. How many architectures can Linux run on? Well, we can take a look, right? We can just go to Debian and look at architecture list. There's actually a pretty easy way to do it. Let me see if this will do it first. If this doesn't do it, we can look at the package, and that will also show us well, there you go. So these are the official ports. Okay, one port is basically one architecture that you can run on. So it goes from the AMD 64-bit instruction set, which ironically, is used by Intel processors. Intel tried to come up with its own 64-bit instruction set when they first came up with what is the name of that processor? The Itanium. Yeah, the Itanium was the first 64-bit architecture native to Intel, and they made an instruction set for the 64-bit extension. But it was so complex and so clunky that nobody used it. And then AMD came up with their own 64-bit architecture and their own instruction set. It was so much better And then later on, Intel just decided, okay, I'm just going to give up and use the AMD version of the instruction set. And then we have ARM processor. We have hard float ABI ARM processor. The i386, which is really great for backward compatibility. IA64, this is the Itanium version, which is also kind of rare because most people do not use this processor anymore. And then we have MIPS, little endian version of MIPS, big endian version of MIPS, PowerPC, and the IBM S390 system. This is also kind of archaic, it's kind of old, and also Sun Spark. The Ultra Spark architecture is now owned by
Oracle.
Oracle, yes. And at one point, the Spark architecture was open sourced, and it is no longer open sourced. So once Oracle, bought Sun Microsystems, let's just say that there was a lot of changes. Especially if you ask all the people who left Oracle shortly after the acquisition. Yes. And on top of that, they have unofficial ports. Okay. So we have the Alpha processor. The Alpha processor is kind of interesting. The Alpha processor was a super processor architecture, and who made that? The Alpha. It's a company that does not exist anymore. Digital Equipment Corporation, DEC. Okay, it's no longer around. Okay, but the interesting part about the Alpha architecture is it is mostly hand designed at the transistor level. So it was a really, really big project for that purpose. AVR32, the AVR architecture is famous for being the main architecture or the main processor used in Arduino projects. We have the HP specific RISC architecture, even the 68000 processor family. Okay, and that's from the fame of early Macs, exactly, like early Macs. The current Macs are using the x86 architecture. The one before were using the PowerPC architecture. This is before that. Okay, but Linux is still runnable on those architectures, probably kind of slowly.
Today, those are actually used in some TI calculators.
They're still in use in calculators.
TI-89 uses that.
Is that the Code Fire architecture now? Because I know they made some changes to that architecture.
I'm not 100% sure.
TI-84 used Z80.
Yeah, the early ones use the Z80. The Z80 processor is also famous because that's also used by Game Boy. Nintendo Game Boys also used the Z80 processor.
In Europe, everybody used ZX Spectrum, it's famous computer in Europe, like first one.
Yep. And then there's a Super H architecture from Hitachi. That's a Hitachi specific 32-bit architecture. So, well, the whole point is not a history of computer architecture or processor architecture. The whole point is Linux, or just the Debian distribution, has ports to support these different architectures, processor architectures. So the question is, why do you think Microsoft needs to hang on to the x86 architecture and insist on binary backward compatibility?
Because they can.
The rights to it.
Because of the way
They own the rights to it, so they can.
Well,
They have it
no,
inside.
they don't. I don't think they own the rights to the instruction set because that's really an Intel instruction set.
It's the NT kernel itself. It's as old as Windows 95. It's been, well, actually, Windows NT 4.0 is when it was first introduced. And that code from Windows NT 4.0 is still present in the NT kernel itself. And it also, the programs that run on Windows, like in a Linux distribution, when you run a program, usually you run 64-bit programs inside of a 64-bit port. On Windows, it has to have the ability to run 32-bit and 64-bit programs simultaneously. And it can't unless that code is still present. So any hardware that's used in Windows has to be backwards compatible all the way back to 32-bit architecture. Whereas with something like Linux, the libraries exist inside of Linux that allows it to run only 64-bit programs.
Well, but the 32-bit, but it's still backward compatible all the way to the 8-bit, 8086 processors. Yeah, you had a. Okay, somebody back there had a hand up. Maybe I didn't. Maybe I saw something. It wasn't there.
Maybe you're seeing things.
I'm seeing things. Yes. Well, what I am seeing here is, basically software engineering challenges. Okay. Now, with compilers, I mean, surely, it's easy to cross-compile something, right? In other words, you run the compiler on one architecture, but the code that it spits out is the object code to run on a different architecture. I mean, that's not rocket science. People have been doing it since almost day one of computer science. That's how they can get the next generation of software ready to run on the next generation of hardware. So the big question is, what is the big holdup with Microsoft products? I mean, okay, if you look at open source products, okay, like LibreOffice or many of the other projects, when you want to port it to a different environment with a different architecture, you just basically recompile it. Okay, you just use a cross compiler and say, okay, I'm running the compiler on an x86 architecture, but the code it spits out, let's say it will run on a PowerPC architecture. And now you have a new version of LibreOffice, not version, but a new port of LibreOffice that will run in using a PowerPC architecture. So that should have been possible with Microsoft products as well, unless there's a big unless. So what is this big unless? There's one thing that can prevent a compiler from helping the cross-architecture approach. And it has everything to do with this class. Hint, hint, hint. Right, exactly. If the majority of a program is written in assembly code, then a compiler cannot help. Okay? When you look at the Linux kernel, there is a portion that is written in assembly code, but it is not huge. Okay? There's a portion, there's a minimalist portion that has to be written in assembly. And every operating system is going to have a part that has to be written in assembly. Linux is no exception, except that portion is relatively small, which means as long as you can rewrite that portion to run on the architecture that you're targeting, the rest of the operating system is fairly portable because it's all written in C, mostly C, maybe a tiny little bit of C++. Okay? Now, if it is all written in C or mostly written in C, once you have the compiler retargeting a new architecture, you just have to recompile the source code, and here you have all the executable ready for the new architecture. So my conjecture is Microsoft has a lot of assembly code in their kernel, and as a result, it's going to take a lot of time to rewrite that portion to support a different architecture. And how long did it take for any operating system to even stabilize, for all the really bad problems to go away? How long did it take for the anti-kernel to stabilize? What was the first really stable version of of Windows that is based on the anti-kernel?
XP.
XP for end users and Windows 2000 Server for server applications. And when did the NT4 kernel came out, or when does the NT kernel came out?
4.0.
No, not 4.0. 3.51 was the first one that was actually in use. So when you look at the Windows NT kernel, and by the way, okay, let me look at the time first, and then we'll talk about what NT stands for. So we take a look at the timeline. Okay, it's pretty easy to do it. Well, I would say it's about 1999, or it has to be before that. Okay, in 1997, somebody wrote this article on Inside NT's Object Manager. So let's say it's 1997. That's a long time. XP came out when? 2002. Yeah, they're about. Yep. So anyway, Yep. Okay, so do you guys still remember why we got into this whole big digression?
No.
Because Ted likes Linux. No, absolutely not. Has nothing, absolutely nothing to do with that. It has to do with registers. Okay? We were talking about the number of registers inside the processor. Okay? And that kind of led to this whole discussion because I needed to point out why, with a modern architecture, the x86 or the i3, 5, and 7 processors can only still have 8 registers. It has to do with hard coding that part into the opcode of the instructions. Okay? So getting back to the notes here, after this big, huge digression, and I think it's over here. I need to put it, there we go. There are also other factors. If all operations connect memory to the ALU, then each instruction must be able to specify any one of the 4 billion locations in memory for the first value, the second value, and so on. So this part has to do with opcode size will be inefficient if we only use memory to store results and only use memory to read from in order to find out, okay, what number am I supposed to work on? Okay, look at this part here. With 8 registers, each instruction only needs to use 3 bits to specify where am I getting the number from, or where am I storing that number to? Okay, it's only 3 bits. So if you say, okay, but each addition operation requires 2 numbers to add, right? Okay, we're going to use up 6 bits. Not a whole lot of width here. If you are going to use memory locations to read from and then to store to, these 3 bits will become 32-bit just to accommodate 4 billion possible locations. And this one will also become 32-bit instead of 3-bit and 3-bit. So now we are talking about 64 bits of one single instruction just to specify where in memory am I supposed to get the number to process and where in memory am I going to store the number that I have just finished processing. Okay? And that's only 32-bit. 32-bit limits to 4 billion bytes, a 4 billion byte address space. How many people in this class have a computer with more than 4 gigabytes of memory? Well, there you go. The next step up is 64. So with 2 64-bit addresses in the instruction itself, now we are talking about 128 bits just to specify where am I reading from and where am I storing to for an addition instruction. Now, why is this bad? Why is it bad to have 128-bit just to specify the locations?
Because that's extremely inefficient, and also you need a third 64-bit just because there's 2 numbers you need to read in, and a third you need to read out.
We assume one of these, is also going to be stored. So one of these operands will be the read-write, kind of type of register. But you're still true that we still need additional bits to specify the operation itself. Okay. But why is this bad? 128-bit, just to specify the addresses. It's a very wide instruction. And why do you think wide instructions are bad from the perspective of efficiency?
Slow.
It's slow because it ties everything back to the memory cycle. Remember the memory cycle? So now we need to go through the memory cycle just to read the instruction in. And when the instructions are wider, each memory fetch can only read a smaller number of instructions. In order to execute a program, now you have to spend even more time on the memory bus just to read the instructions in. Okay? Now, when you look at the instructions that you're reading in, what do you think is the regularity or linearity of instruction execution when you're executing a program? In other words, do you think the burst mode read operation is going to be beneficial when you're executing a program? The answer is
yes.
It depends. It depends, because if you have a lot of subroutine calls, it's not going to be beneficial. Because the subroutine that you're calling is unlikely to be right next to you.
But when you have arrays?
If you're processing arrays, it depends on what kind of processing you're doing. For instance, quicksort. Do you think quicksort can benefit a whole lot from burst mode memory read and write? Nope. What about merge sort? Okay. Even bubble sort. Okay. Bubble sort has a great deal of locality, even though it really sucks from the algorithm complexity perspective. In terms of locality, there's a whole lot of locality because you're just doing very close. You're doing processing right next to each other. But when you look at binary search, what about binary search? Does it have any locality? How many people still remember what binary search is? Okay, I'm hoping the rest is just shy. Okay, binary search means you start with a huge stack of cards, okay? And the way you search for the item that you're looking for, assuming this is already sorted, the way you look for the one that you want is you pull a card from the middle, okay? Right in the middle. And then you use that card to compare to the value that you're actually looking for. And there are only 3 possible outcomes. One, this is your lucky day. That's the number that you want. Unlikely to happen, okay? So the other 2 choices is it is either larger than or lower than, larger than or smaller than the value that you're looking for. But in either case, you can eliminate one half or the other half of the remaining choices. So with the half that is remaining, you apply the same technique, same technique, same technique, same technique, same technique. So you can zero in to the entry that is closest to the value that you're looking for to either confirm, yes, the number that I'm looking for is in the stack, or you can confirm that it is not there. And it's a very fast search algorithm. The complexity is a log time. If the number of items is n, the time complexity is log n, which is a really, really fast algorithm. But in the context of what we are talking about here, it does not benefit from burst mode read operation, because the burst mode read operation will read this location and a little bit after that. It's not going to be helpful, right? Because the next location is either all the way down here or all the way up there. So that's why whether DDR5 is going to help you depends on a lot on what kind of program you're running. Depends on memory access pattern. Okay? And we haven't even talked about caching yet, because that's another technique that can help speed up processing. And basically it's kind of like, instead of going all the way to the library, I have a small cache of books that I can keep outside of this classroom. So it's still outside of the room, which is the processor, but it's not nearly as far away, as the library. So that's why caches can also help to speed up modern processors, because we really have a lot of processing power inside the chip. The question is, how can you feed the chip fast enough so that it can keep up with all the processing potential of that hardware? Any questions?
So cache is inside the chip? Cache is inside the chip.
The cache used to be outside of the chip, but it is definitely still outside of the core. These days. It depends on which level too, because we have L1, L2, and L3 cache now, whereas before there's only one cache, right? I mean, how many people are old enough to remember that when you have the 386 processors, the cache you can actually populate the cache with individual chips. I remember that. Yep, many of you look at me like, wow, really? You can buy individual chips to populate the cache, and yes, you can.
When they did slot 1 form factor, it was improvement because cache was on the same plate with processor on a slot. It was much closer to a core.
Yep. And those were the days when we still have a through-hole parts on a circuit board too. All right, so we are running out of time. I'm just making sure that you guys understand the general principle, because I want to explain, why we have registers instead of just memory. Because, otherwise, why don't we just use memory? Why do we need these extra things called registers? And of course, I forgot the row sheet today. All together.
You didn't even bring it.
Huh?
You didn't even bring it?
I brought it. I brought it here, and I put it here just so that I can see it, to remind myself I need to take row, and guess what happened?
Take a marker.
No, I need to write on your forehead, so when I look at you, I go like, oh, take roll.
Make that your password.
Take roll.
Student